Hello,
Hello,
how are you doing?
I'm doing good.
Sounds okay.
It's a little quieter today.
What about now?
Yeah, now it's good.
Okay, great, thanks. Okay, let's let everyone through. Hi, everyone. Uh, Noise. What can you do? Okay, hi, everyone. Before we start, if there's any questions, let's have them now.
Yeah, so long tie. Go ahead.
Yeah, I want to confirm, so we have only one basis for each Jordan block. Is that right? Can we say that? Because we have like one eigenvalue.
Try to tighten up your question. Tighten it up a bit. What are you talking about?
We only have one basis. Like,
Try to formulate it into a question. What are you asking? Are you asking whether we're
So each
looking for a
Jordan block
unique
is
basis, that there's
linearly-
only one specific basis and there's not many possible bases for the Jordan description?
Yeah,
Or?
I think so. Yeah.
So let's go back to the simplest case. So what's the simplest diagonal matrix that you know?
Identity matrix.
Well, even simpler.
Or zero matrix.
Okay, so does it depend on the basis? Which basis?
Nope.
Which basis is it zero?
It doesn't depend on. I think all of them. Sorry.
So if you take the zero operator and you write it in any basis, what is the matrix?
It's just zero.
And what about if you use the identity matrix? The identity operator, sorry.
Or we just saw one on the.
Yeah. So you see that the basis is not unique. There's many bases that you can use to put something in Jordan form.
Right. But there will only be one eigenvalue associated with one each Jordan block.
So the thing is, what I'm trying to do, I'm trying to answer your question in a way that will teach you something. Okay, so you have to take those questions and you have to try them out on the very simplest possible example. Right? Don't look at this and say, oh, start asking questions about this. No, I gave you several simpler versions of this, right, to test out your questions. So that's what you should do.
Yeah.
That's what I mean when I say you have to meditate. It means you have to ask yourself questions in silence, and then you have to try to answer them. And if you can't answer it, then you make the question simpler and you ask yourself again. And, in this way, you will eventually reach nirvana. Okay, next question.
Thank you.
All right. So Jack has a question.
Hi, Professor. I was just kind of wondering in general, honestly, like what the significance is of being able to represent matrices in terms of, these sort of fixed points, these eigenvalues and eigenvectors, and then having cycles, and whether there's like something kind of deeper that this sort of idea is related to that maybe we'll talk about at some point, but I was just curious.
So, what do you think is the most important scientific discovery of the 20th century? What do you think it is?
Oh, man.
In terms of applications and impact on future humanity?
Probably the internet, maybe?
Yeah, maybe. That's possible. It remains to be seen. Right now, all we have are memes and a bunch of misinformation. What's one discovery that will genuinely transform the human race as an actual species?
Computers.
Well, yeah, I agree. I agree that computers are one of them. And the other one would be DNA.
Oh, okay, sure.
It would be the discovery of the source code underlying, biological evolution, right? It's essentially the information store of how life evolves, right? So once we understand the fundamental building blocks, the fundamental nature of the information that is contained inside an organism is that it's encoded in this DNA, right?
Right.
So this is what it is. This is what you're looking at here. This is the DNA of a general operation, a general operator.
Right.
Any operator can look very complicated when someone gives it to you, right? It can look extremely complicated. And your job, if you want to understand it, if you want to use it for a purpose, if you want to extract information from data, what you need to understand is not the particular numbers. The numbers are irrelevant. The numbers in the matrix, right? They depend on the basis. But these numbers that I've written here, right? They don't depend on the basis. And the number of cycles and the size of the cycles, those are fundamental. Those never change.
Right. So like, yeah, the thing that I was just kind of wondering as well was just like, as the mathematics becomes more abstract, does this sort of DNA sort of building block stay the same? Like, can we still represent sort of like, more abstract mathematical structures in terms of like cycles and then like fixed points?
Well, the more complicated the more complicated the structures are, okay, the more complicated the fundamental building blocks are. But the point is that there are very much similarities, right? Like you see how I explained that you have finite sets and you have vector spaces, and they have very similar fundamental building blocks when you're studying maps from the finite set to itself, right? So that's an example of two completely separate categories which have very similar DNA. Okay.
Right.
And the point is that every species is different. Every plants have a different type of encoding in the DNA, groups, rings, fields, whatever, all these things, they have different ways in which the building blocks are made up, right? So what's important here is two things. First of all, these operators are actually used for many applied problems, and you need to know how to deal with them from a fundamental level. But second of all, for abstract mathematics, there's many categories out there of increasing complexity, and each one of them has fundamental building blocks, and the way that you analyze them is similar to the way that we analyze this. It's just that it gets more and more complicated.
Great, thank you.
You're welcome. There is a reason why, these classification theorems are taught, and it's not just because they are extremely useful themselves. It's because they're a model for how you evolve, later on. Well, okay, these are deep questions always. Okay, so let's just review, okay, quickly what we did so far. So okay, so the first thing was that we found a polynomial. We found that there is a polynomial that kills the operator t. Okay, there's many such polynomials, but they're all multiples of a single polynomial, which is called the minimal polynomial. Okay, so right now, I haven't given you a method for computing that minimal polynomial. Okay, but we're going to get there soon enough. Next week, I'll explain the method. The basic method is that you first have to find all the eigenvalues, and then you need to test. You need to well, the book goes over this in detail, but I'm going to explain it next week, how you obtain the minimal polynomial. There's an easy polynomial that you can get, which is called the characteristic polynomial, which always has degree n, the same as the n by n matrix. So that one's easy to get, but the problem is that it may not be minimal. So you might want to test whether you can remove certain factors in the characteristic polynomial to reduce it to being something that still kills the operator. So you just do that systematically and you produce the minimal polynomial. Okay, but anyway, we have this minimal polynomial and we're going to use it because we're going to say that this polynomial, first I'm going to factor it because I'm going to work over the complex numbers. So I factored the minimal polynomial and I get I get these linear factors raised to powers. Okay, and then so this when I plug in t for z, this polynomial in t will be 0. That's the idea, right? So we start with a polynomial that kills t. Okay, but then we're going to look at each individual factor, t minus lambda I to the ni, and we're going to look at what that kills. And we're going to call that vi, and there's going to be a certain number of these depending on how many eigenvalues there are. So we have these different null spaces, and the theorem, the decomposition theorem, is that v actually decomposes into the null space of these pieces of the minimal polynomial. So what that means is that if you take a vector in vi, right, what this means is that if you apply t minus lambda to it, so let me just make a comment about this null space. So comment about the null space of t minus lambda to the I, or let's say null space of t minus lambda to the n. And let me vi t minus lambda I to the ni. So let's see. So first thing I want to observe about this is that it is an invariant subspace. What does this mean? It means that if we apply t to it, it stays inside there. It stays inside the vi, as we discussed before. So t applied to vi is contained inside vi. Why is that? Well, okay, if I take u inside vi, this means that t minus lambda I to the ni applied to u is equal to 0. Okay, so then I want to check that t of this vector, tu, I want to check that it's in vi. So what do? I just take t minus lambda I to the ni and apply it to this and see what I get. But remember that t commutes with t, and it commutes with a multiple of the identity. So it will commute, t will commute with all of these powers with all these products, and I can bring it to the other side. Oh, t minus lambda I to the ni u, which is equal to t applied to t minus lambda I to the ni u. So it is equal to t of 0. So if you take a vector in that is killed by t minus lambda I to some power, then when I apply t to it, that vector is also killed by t minus lambda I to the ni power. Okay, so what does this mean? This means that we have found a subspace which the operator just acts on by itself. Okay, so it's minding its own business inside this subspace. Okay, and so that means that we can, if we can separate V into a sum of these subspace, a direct sum, then all we need to do is analyze the operator on each one of these subspaces, and then we're going to know what the operator is on the whole space. So in other words, so this implies that if V is the sum of these VIs, and what is it, NK or K? K. Okay. We can understand T on V by studying T restricted to VI for each I, for all I. If we know how T acts on each of these individual pieces, then we're going to know how it acts on the whole space. So that's the first kind of important part of this. Now these things are called, so this VI, this is called a it's called the generalized eigenspace of with eigenvalue lambda I. Okay, so why is that? Well, okay, so so let's say here's here's the cliff, and here's the abyss. Okay, and here we have the nice the nice let me try here. Might as well do it properly. Here's the nice green where all the lemmings live. Okay, and we're looking at VI, which is the null space of T minus lambda I to the, sorry, let me write that again. We're looking at VI, which is the null space of T minus lambda I to the Ni. Okay, so what do we have inside this null space? Well, we have some vectors. Okay, we have some vectors which are sent by T minus lambda I directly into the abyss. So if I apply T minus lambda I, they all jump off the cliff. What are these vectors? What are the vectors that are killed by T minus lambda I? You know them well. What are they?
The eigenvectors?
The eigenvectors. Okay, but there are some people who are not. Let's just see. I want more eigenvectors. Let me put another one in there. Oh. I need some more. These are the eigenvectors. Okay. So here we have, I'm going to use this diagram to indicate that it's a 1, 2, 3, 4, 5-dimensional eigenspace. Okay, but there may be some other people here who are not let me remove, yeah, who are not eigenvectors, but it takes t minus lambda 2 times to kill these. So after one step, they get moved to the front row. So these here are not eigenvectors because t minus lambda I does not kill them. Rather, all that t minus lambda I does is it moves them to the front, okay? And then the next step, they will be killed. So these are generalized eigenvectors. Okay, and then there might be some more vectors here, and there might be some that are in a very long chain. Okay, so all of this is happening for a fixed eigenvalue. So this is like the, lambda I fixed. So what the Jordan canonical form is telling us, this is related very closely to the Jordan canonical form, but the fact that I have the null space of t minus lambda I to the ni, the fact that, for example, if I count the length 1, 2, 3, 4, 5, 6, 7, 8, this means that for this example, t minus lambda to the 8 will kills all. Okay, so there are some eigenvectors, but then there are some people behind them, which are generalized eigenvectors. All of these are generalized eigenvectors. Okay, and the only sense in which this diagram is not accurate is the fact that there's not a preferred choice of these eigenvectors because they all have the same eigenvalue. So really, it's really just a 5-dimensional space sitting here. And we don't have a preference for which which vectors to choose there. So this is going to Longtai's question from before, right? There might be 5-dimensional space of lambda I eigenvectors, but there is no preference for which 5 to use as a basis. You could literally use any basis for this 5-dimensional space, and all of those bases, they would consist of eigenvectors. And so then what we need to do, what we would like to do is, so here's the trick. So here's the kind of the challenge. The challenge is to choose a basis for VI, which behaves nicely when we apply t minus lambda I. Okay, so what do I mean by this? Well, you see here there is a 5-dimensional eigenspace. Okay, and I can choose my basis for that eigenspace however I want. Okay, I could let this be a basis vector, this be a basis vector, and then I could choose, for example, some linear combination of these and these to be my other basis. But here's where the problem comes: that these two vectors, they don't have anyone behind them, but these 3 they do. Okay, there is some subspace which has people behind. They have vectors which are generalized eigenvectors that will be sent to them. Okay, so I want to make sure that when I choose my eigenvectors, I want to make sure that the choice that I make for my basis is a choice that, like, I don't want to choose it at this stage. What I really want to do is I want to choose at this stage. I want to choose this one. Oh, that's invisible. I want to choose this one, and I want to choose this one, and I want to choose this one. Because if I make this choice, okay, then by applying t minus lambda I, it will produce for me another vector. And if I apply it again, it will produce for me this vector. So I only need to make this choice once, okay, and it will generate all of these vectors just by applying t minus lambda to that choice, right? If I chose it at this stage, then I would have to make this choice, and then I would need to make another choice and another choice and so on, right? So I'm just trying to explain the way that you choose a basis so that when you write the matrix, it looks like, it looks organized, so that each vector will be just sent to another basis element and another basis element and so on. So really the procedure will be that that you need to you need to figure out a procedure that will permit you to pick the safest lemmings, you know, the ones that are furthest inland, that are not eigenvectors, but they will become eigenvectors eventually. Okay, you want to get them while they're young, before they get too close to the edge. Okay, so that they will generate a lot of vectors, you know, progeny eventually, and then so you have to make the fewest choices possible. Okay, so so let me just explain how this choice is made. So I'm kind of skipping some steps. I'm skipping the proof of the decomposition theorem, but I just want to present the whole logic, and I'll worry about the proofs next week. So let me just give you the complete logic. So first of all, we find the minimal polynomial. We find any polynomial p of z such that p of t is equal to 0. Number two, factor it. We're going to get z minus lambda I1 to the n1, z minus lambda ik to the nk. Number three, decompose V as a direct sum of k parts, which are completely independent. They're direct. It's a direct sum where Vi is the null space of t minus lambda I to the ni. What was my notation before for the lambda i's? It was just I. I don't need an I1. 1, k. Okay, so we decompose this. So this I still need to prove. I still need to prove that. Okay, and then choose a basis for each Vi according to the following procedure. Okay, let t minus lambda I be n. I'll call it n because it's nilpotent. Because if I raise it, oh, I'm sorry. Let me make this a little bit more precise. Let n be t minus lambda I, okay, restricted to Vi. So this makes sense because Vi is an invariant subspace. So it's sent to itself by t, and of course by the identity. And so it will be sent to itself by this operator. But the reason that I want to give this operator the name n is because this one, n to the power ni, is 0 on vi. So it's nilpotent. Okay, and I don't want to label it with an I, because it's the same procedure for each of the VIs. The particular value of the eigenvalue doesn't really matter for the rest of the procedure. The important thing is this nilpotent matrix, the matrix that raised to a certain power will be 0 on VI. Okay, and so I need to explain what the procedure is. So I'm gonna get to your questions in a second, but I just want to explain this procedure so that will be done at least with the logic of the whole thing. Okay, so someone's mic is scratching here. Okay, so so let's draw a picture of this. I'm going to draw a slightly different picture, which is maybe less sadistic. I'll draw a picture of VI. And we'll copy it again, and again, and again. Okay. And I'm going to draw a picture for, this is a picture for ni equals 3. So what I mean here is that if I apply n 3 times, I'm going to get 0. So this is an example of a nilpotent of step 3. Okay, and if this is 0, then what I get is a picture that looks like this. Okay, so that on the first step, all of VI is mapped to some subspace of VI. And after the second step, it's mapped to a certain smaller subspace of VI. And then on the third step, it's mapped to the 0 subspace. So this, yeah. Okay. So I'm just trying to draw a picture of, what you get when you apply n several times. So comparing with our previous picture, right? This here, what are these elements? There's something special, you know them well. What are these elements? These are the elements that are killed by applying one n, just a single time. So what are these?
Eigenvectors.
Yeah, eigenvectors with eigenvalue I. And all of these are all generalized eigenvectors. Okay, so, right. Okay, and then what about, so how would I describe these eigenvectors with eigenvalue I? This is the null space. Oops, sorry, that's a bit. This is like the null space of t minus lambda, of null space of n. But this one here is somehow, this is the null space of n to the 3. And this one here is the null space of n squared. Okay, so the further I get from the abyss is here. Might as well. 0. Okay, and the further I get, this is first row, they will die immediately. Then the next ones, the null space of n squared, these are the ones that have 2 time steps to go, and so on. So basically, you know, yeah. Right. Okay, so what do we want to do? We want to choose a basis which is as long lived as possible, so that they will generate many, many children. Okay, and that means that I don't need to make a choice of all those basis elements. The applying n will just create them for me. Okay, so how do I do that? Well, I don't want to choose anyone in here because they only have 2 steps. And what I want is to choose someone out here, someone who is not in the null space of n squared. Okay, so let me explain the procedure for n equals 3. So so first find the null space of n to the n minus 1, which in this case is n squared. This is these are the vectors that only live n minus 1 steps, and they do not live n steps. Okay, so these are rejected from our choices. We do not want to choose these people. Okay. Okay, and what we want to do is we want to choose vectors which are not in this space. So the correct way to do this is maybe to choose a basis for this, choose a random basis for null space of n minus 1, and extend it to a basis of vi by adding e1, e2 up to ek1. So these are the good ones. We don't care about the choice of the random basis for this null space of n squared. What we care about are the extra basis vectors that we needed to add, because those these ones, they live out here. That's where e1, e2, and so on live, which means that they are out here, right? Because this is the same space. The vi is just repeated here. So maybe I'll put the label here. Okay, so in other words, yeah, so these ones, okay, in order for them to die, I need 3 steps. 2 steps is not enough. Okay. Then the next step is that we generate all their progeny. You know, for E1, we produce n E1, n squared E1, and so on, all the way to what's the last one? In this case, it would be, in this case, it would just be n squared E1, or n, because they would be mapping, you know, we would have E1, n E1, and n squared E1, and then 0. Okay, so it has to go 1 less. So it'll be n to the power n minus 1 E1. And we do the same thing for EK. Okay. What we've done, therefore, is we've produced now, we've chosen this one, and we've generated all these. this is the result of step B. So this is step A, and this is step B. We get the entire line that is, marching into oblivion. Okay. And so what that means is that now we can forget about this line completely and turn our attention to the remaining people and do the same thing again. So now we repeat. Oops, sorry. See, we repeat procedure for the null space of n squared in the next step. So we need to find, not null, null of n to the n minus 1. So we have to find,
Wait, shouldn't it be for the null n to the n minus 2?
Just 1 second. So we repeat the procedure for null space of n to the n minus 1, right? In the sense that this is now playing the role that our original space played. So now what we're interested in is we need to find the longest lived elements inside here, inside the null space of n squared. So how do we do it? Well, first we find the ones that are not the longest lives. We have to find the null space of n of, we need to find the null space of n to the n minus 2, choose a basis, and extend to a basis for null n to the n minus 1 by adding, f1 up to, or I need another, what you could do is just put a 0 index here. Actually, I'll take that back. I'll put a 1 index here. First step. Okay, the second step will be E2, right? 1 up to E2k. Okay, and so these ones now, let me color them pink, let's say. They are the choice here. So this is the choice of E2i. Okay, then what we need to do is generate their progeny. So we need to do the next step. Find progeny. So we take E12, we map n. We get new vectors n E12. Okay, and we need to do one fewer. So we go n to the n minus 2, E12. And we do the same thing for EK2. Okay, and we just continue this. For all steps. Okay, and at the very last step, in this case, would be that you see what happens is that after 3 steps, that means that I've gotten this long line, this shorter line, and this shortest, even shorter line. I've gotten all this part of the vector space. The only thing that I'm missing is a couple of eigenvectors, something that is killed in one iteration. But notice that because of the way that I built it, I already have a partial basis for the eigenvectors. So I just need to, yeah, sorry. I need to correct one thing. Yeah, sorry. There's one small correction I need to make. It's in the second step. So let me explain what is going on. So in the second step, right, what I said is, well, okay, technically here we would be looking at n to the, 1, 2, 3, 4, 5, 6, 7, 8, let's say, and you would do n to the 7, n to the 6, n to the 5, n to the 4, n to the 3, and then at n to the 3 you would find an additional vector. Now, what you need to be careful of is the following fact. So if I look at the null space of n to the 3, okay, it will contain this element, but it will also contain an element from the previous step that was mapped there, right? So when I make my choice of a basis for the null space of n to the 3, I need to make sure that I do not choose something that has already been chosen before. So that's what we need to just ensure here. So let's see. Find null of n to the n minus 2. Yeah. Inside the null space of n to the n minus 1. So these are the ones that are not long-lived enough. Okay. Add to this the image of, add to this the range of n, add to this the span of n e1 up to n ek, because you see, when I chose the longest lived elements, when I apply n once, they're going to give me a bunch of stuff that is inside the null space of n to the n minus 1. And basically, I don't want to choose those either, right? I don't want to choose basically anything that is too short-lived, but I also don't want to choose anything that came from applying n from the previous step, right? As long as I avoid those two possibilities, then I'm okay. So, and then extend to a basis of null n to the n minus 1 by adding E2 up to E2. Sorry, E2, 1 up to E2k. Okay. So that's what happened. So basically, just to show it in a picture, what's happening at this step is that I'm looking at this huge space here. Maybe, right? All of these are sent to 0 by applying n 3 times. But I do not want to pick any of these. because they're too short-lived. And I also do not want to pick this one because I've already produced it from the previous step. That's what is going on here. So that's why I need to avoid this null space, which are the two short-lived. And then I also need to avoid the result coming from the previous step. Okay, and as long as I avoid those two, then these are new. These are new stuff, which are exactly the right age. Okay, and then you generate their progeny, and you just repeat this procedure. Okay, so in the end, okay, T restricted to well, okay, let me put it this way. N restricted to VI has the following matrix. So E1, E12 up to E1K, where okay, so we're going to order the basis now in the following. I remember that a basis is ordered. So maybe the last step is D. No. Last step is 5. No, it's okay. I'll use D. So for D, we order the basis as follows. We take E1, we take its progeny. Okay, then after you're done, you put E12 and you put its progeny. Okay, and once you've done all those, then you do the 2, E21, its progeny, and so on. Okay, so it's basically you just produce them in order. You just put a vector in and all of its progeny, then put the next vector, which is the longest lived, and you just order them that way. So you put you get a big list. And if we now write the matrix of n, right, then what do you see? Well, okay, well, let me just continue. I see that there's a slight ordering difference from the way that I described the Jordan canonical form, but what's going to happen? The first basis vector is going to be sent to the second. The second basis vector is going to be sent to the third. Okay, and so on until we get to however many progeny it has. Okay, and we've got one block. I drew the Jordan blocks to have the ones on the upper diagonal rather than on the lower diagonal. Sorry. The way that I set up the ordering here is that it's going to be lower diagonal, but that's okay. Some people draw the Jordan canonical form with the ones just one below the diagonal. Okay, the next is going to give me another Jordan block. Okay, and we're going to continue that way. We're going to get smaller Jordan blocks depending on how long the line is before the oblivion. Okay, so we're going to get a bunch of these. Okay, and then therefore T, which is n plus lambda times the identity, will just look like it should. Okay, so this is so we don't really have much more time, but that's the complete logic. So we need we need to find a polynomial that kills the matrix, kills the operator, factor it, use the decomposition theorem to separate our work into different eigenvalues and treat them all separately. For each eigenvalue, you produce this. The key is to consider this nilpotent operator, n, which is t minus lambda. And then you just organize this thing into, it's like a bunch of lemmings running off of a cliff. You just need to organize it in a certain way so that when you're done, you get a matrix that looks like this. And then you have a genuine kind of understanding of the type of behavior that this operator is doing. Of course, most people just try their luck at a casino. A lot of people gamble, even though it makes no sense. The equivalent of gambling in this game is to just assume that your operator is diagonalizable and that all the Jordan blocks are of size 1. And that's what a lot of people do. And and if you do this, then, well, I can't help you. It's just not true. Okay. Next week, we'll go over the fundamental result that we need to prove this theorem, which is the decomposition theorem, but basically that explains the Jordan canonical form. Okay, I'll take questions going into the office hour.
All right, so Jack has a question.
Hi, Professor.
Hi.
Thanks for the lecture. I'm sorry if this is something that you're going to address next week, but how exactly do we know that the elements that we find here form a basis?
Well, okay. So if you think about the way that we did it, they have no choice but to be a basis. Like, for example, the way that I chose it was that I said, okay, I want to choose a basis, and I want to start by choosing some elements which are not killed in 2 steps. So what I do is I figure out a basis. I just choose some random basis for this smaller set of undesirables or young. I'm not sure how to call them. Maybe they're like too old, in a sense, right? So you figure out what the older people are, right? And then you extend your basis by choosing a basis for whatever remains. Okay. So now I just remember those young basis elements, and I keep them in my list. Okay. But that's only that's not a basis for the whole V, right? The problem is that it's only going to span a subspace which is complementary to the null space of n squared. So I need to now choose a basis for the null space of n squared. All right, and then the way I do that is I do the same thing. I eliminate the ones that are too old. I extend to a basis of the null space of n squared, right? And now I have a basis for a little bit more. And the way that we're doing this is that we're just extending and extending until we get the entire space.
Great, that makes complete sense. Thank you.
You're welcome.
Okay, so Andy has a question.
Hello. So can you scroll down a bit to the end? Like even further. So since the matrix restricted to VI is that.
Yeah.
So this matrix would also be T restricted to VI with and then we would stack those
That's
T
right.
restricted to V1.
That's right. This would be T restricted to VI, correct. So you're going to get T restricted to VI.
And then we would get the Jordan form as before,
V1,
like the full Jordan form
V2,
with all the eigenvalues.
Yeah, that's right.
Okay.
You need to put all the eigenvalues together. We separated, the way we analyzed the problem was to separate each eigenvalue is separate, it's treated separately. We choose a basis for each one of those. And the point is that the decomposition theorem says that
it's a direct sum.
Yeah, if we choose a basis for the V1, for the V2, for the VK separately, then they will form a basis for V. Yeah.
Okay, thank you.
You're welcome.
So Lauren has a question.
Yes, Professor.
Hi.
Hi. Could you go to the proof that VI is invariant?
Yeah.
Yes. So in the second line, why we can commute T with T minus lambda to the n.
So don't all operators commute? If you take two matrices, A and B, don't they commute? AB equals BA, right?
Okay, I'll think about that. Thank
No,
you.
no. What, do you agree with me or not?
Now I can see that.
So do matrices commute or not commute? It's one of them is true, right? Which one? So so these are operators, right? And they don't commute. Do you agree?
Yes.
Okay, so the reason that you're asking the question is because operators don't commute. And so you're wondering, how did I commute those operators, right? Is that right?
Yes.
Okay, so if I give you a random operator, T, okay, can you give me one operator that it will commute with? Just what's the simplest possible operator?
Identity.
Yeah, everyone likes the identity. No one likes zero. Does T commute with the identity?
Yes.
Why?
Because it's equal to T.
Yeah. What about zero?
Yes, it's also commutable because it equals 0.
Okay, so give me, now that you've given me the two simplest ones, give me one other matrix operator that you're guaranteed T will commute with. What if T has an inverse? If T has an inverse, it would commute with its inverse, right?
Yes.
So T minus 1. So that's a non-trivial operator. Why do they commute?
Because of the definition of the inverse.
Okay.
Because the product is the identity.
Okay. So now give me another one. Give me another operator that commutes with T automatically.
The inverse of T plus lambda I.
Yeah, well, yeah, because you're taking I already have I already have T inverse, so you can take the sum of anything that commutes with T. It will also commute with T. So yeah, what you said is correct, and it's a consequence of these two because you're just adding these two together.
Yes.
Okay, so can you give me another one that's not on this list? What did I give you in your hand? What do you have in your hand? There's not much. I gave you 0. I gave you the identity. What's the only other operator that occurs on this page?
T itself.
Thank you. Thank you. Is that okay?
Yes, I see. Thank you.
Okay, you're welcome. Sometimes
All
these
right.
things are painful. You got to go through some pain.
So Daniel has a question.
Hi, good afternoon, Professor.
Hi.
I am a little confused. It feels very mystical to me, this process. I was hoping that you could do some sort of finite dimensional example. The very simple matrix that you can apply this to. Or some sort of V that you could apply this to. I'm just a little confused.
One second. There's a nice example that I'm going to do later in class, so I'm not going to do that one now. But
Can you take the identity and decompose it into its basis vectors? Just the spans of those? Is that a simple example? I don't know how that would pan out.
okay, so let's be a bit careful. So you have to understand that most operators that you would write down, they are diagonalizable. Okay, which means that you can find eigenvectors v1 up to vn, so that the operator is very simple. You just apply it to the basis element and you get a number, right? So that's what this indicates, right? So we have a basis E1, E2, E3, E4. I apply the operator to E1, I get lambda 1 E1. Okay, so these are 1 by 1 blocks. Okay, so most operators will be of this type. And none of what I said after would be necessary. None of that work would be necessary because they're all eigenvectors. Okay, so the identity matrix, you choose a basis. The matrix of the basis will look exactly like this, with all of these being 1.
I see. So no further work would be needed for that. So
Yeah.
is this process far more complex? Something that doesn't have like 1 by 1 blocks?
Yes. This whole process is for matrices, is for operators and matrices, which are not diagonalizable. They don't have these fixed point type behaviors. Okay, they're more complicated. So there's two main things that you need to understand. First is that these things exist, right? So for example, if I take a matrix, because the first thing that I did in this whole part of the class was to show you that these matrices exist. Like for example, if I take the matrix 1, 1, 0, 1, okay, this is a quintessential non-diagonalizable matrix. And it doesn't have anything to do with the field. Okay, just look at what it does. It's obvious what I'm claiming, right? So we have E1 and we have E2. These are the two basis vectors in R2. Okay, what does the operator do to E1?
It sends it to itself.
Therefore, E1 is
invariant.
Well, E1 is invariant, but it's has a more famous name than that.
An eigenvector.
Yeah. With which eigenvalue?
1.
What about E2? Where is it sent?
Sent to the diagonal between E1 and E2.
Okay, so that means that you were not successful in finding another eigenvector. Can we choose another vector, maybe? Can we find another vector which is sent to itself?
The zero vector?
Okay,
Yeah.
but I mean, zero vector is always sent to itself.
Yeah.
I mean, that's not an eigenvector. Zero vector doesn't help you decompose or understand anything because it's always sent to zero. In the definition of an eigenvector, it must be non-zero. You need it to actually span an actual subspace. So, I mean, what was the reason that we couldn't pick E2 as an eigenvector?
Because it's not sent to itself?
Because T of E2 is E2 plus E1.
I see.
Now, what if I take some other combination? What if I take, E1 plus, let's say I take some combination A E1 plus B E2, and I want it to be an eigenvector, so lambda times A E1 plus B E2, right? So what is this going to give? This is just going to give A E1 plus B E1 plus E2. So then I'm going to get lambda A minus A E1 plus lambda B, minus A minus B E1 plus lambda B minus B E2 is equal to 0. Did I do that right? Daniel, did I do that right?
It looks like it's right.
Okay, so what happens if we try to solve this? Both of these have to be 0 because E1 and E2 is a basis. So I need that lambda B is equal to B. And I need that lambda A is equal to A plus B, or lambda minus 1A is equal to B. Okay, and the thing is that that I want this second vector to be linearly independent from E1, right? E1 is already a basis element. I need to extend it to a basis. So I want to choose something that is not E1, right, in order to build a basis. So that means that the B should be non-zero. So I want B to be non-zero. But then this would imply that lambda is equal to 1. And then this would give me 0 is equal to B. So it's a contradiction. I cannot find another eigenvalue, another eigenvector. Okay, now I gave you an algebraic proof. That's not very illuminating. Okay, if you wanted to have a better idea, just look at what this operation is doing. It's taking a vector and it's moving it this way, right? It's moving everything this way, and everything on the bottom is moved this way. This is what's called a shear transformation, right? So the whole vector space is being sheared with only one direction, which is sent to itself. The horizontal direction is sent to itself. Everything else is sheared. So you will not be able to find an invariant subspace, which is transverse to the, which is complementary to the E1 subspace. The point is that there are transformations like this, these shear transformations, and we need to be able to analyze those. That's the purpose of this whole subject of Jordan canonical form.
I see. Yeah, so nothing would be sent back to E2 because of this transformation. It doesn't matter how much we scale to the right, above the axis, and below.
Yeah, correct. So then the analysis proceeds like this. If I have this matrix, then what you do is the minimal polynomial is what? It's T minus 1, T minus the identity. That doesn't kill, so this is equal to 0, 1, 0, 0. But this one is nilpotent. Those wonderful people who have the potential to be 0 if you just square them, right? If you square this, you get 0. So we have a polynomial, a quadratic polynomial that is the minimal polynomial for t. P of z minimal is t minus 1, z minus 1 squared. So that's the first step, is that we find the minimal polynomial. Okay, and then we look at t minus 1, and we call this n, because this is the thing that's nilpotent. And we study this one. Now we go to the cliff. The nilpotent people, they are working at the edge of the cliff, and they're making the lemmings go over the cliff. So what do? We say, you know, there's a two-dimensional space. For God's sake. Okay. V is two-dimensional. I apply n once. It's a map from V to V. I apply n again from V to V. I get 0. So everything in V is sent to 0 when I apply n twice. Okay. So what that's going to tell me is that, you know, when I choose my basis, what I want to make sure is that the first basis element that I pick should be one of the longer lived elements. I want to pick a vector which is not in here. So the first basis element should be one of the long-lived vectors, which are sitting in the back, that are furthest away from the cliff. Okay, that means that I want to pick something in here, but which does not lie inside the eigenspace. You know, E1 is living right here. E1 is right in here because it's killed by n on just one application. It's an eigenvector.
So we want to choose E2 in that case?
So the point is that in the procedure, we choose E1. This is a basis for the null space of n. And then we extend to a basis. Well, okay, let me call it a different thing. I'll call it F1 is a basis for null n, and extend to a basis for V by adding some other vector. E11 is what I called it in the procedure. So this E11, where is it? It's right here. It's outside. E11 is out here. And that's the first thing that I want to use. I forget about F1. I only used it to get to my goal, which was to choose this E1, which was one of the longest lived vectors, the one that has length 2. Okay, and now once I have that, now with E11 in hand, we generate the progeny. We take E11 and then we apply n to it. And we call this the first basis element, E1, and this the second basis element. Okay, so in this case, what would it be? It would be like 0, 1, 0, 0 applied to 1, 0. This is E1. No, sorry. Let's do it more carefully. So we need to check, we need to pick, so this is in the null space of n because 0, 1, 0, 0 applied to 1, 0 is equal to 0. Okay. Then I need to extend to a basis. So I need to add another vector to this one, which makes a basis. Well, okay, the simplest choice would be 0, 1, but it doesn't have to be 0, 1. I could pick something else. This is my first genuine basis element.
And this is for a basis for V?
Yeah.
Okay.
Okay. So so far, you know, I got one basis element, and I need to now produce the progeny. So I take the operator 0, 1, 0, 0, and I apply it to this choice. I chose this. Okay. And then the progeny is this one, which is exactly 1, 0. Okay, so then, so now I've got it. E1, 2 is this one. So now if I apply, yeah, so you can see how, actually, let me just do this example with a different choice. That might be helpful. So let's say I choose 1, 1. Together with this still forms a basis.
Yeah, I agree.
And then what I can do is I need to produce the progeny of this one. So I need to apply this to 1, 1, and I'll get 1, 0 again. So now I want to write the matrix. So I have a basis, which is 1, 1, and 1, 0. And I want to write I want to write my matrix T in the basis beta, beta. Okay, so if I check that out, what happens if you apply T to 1, 1? Well, T was 1, 1, 1, 0. This is going to give me 2, 1. And 2, 1 is the sum of these two basis elements. So this is 1, 1. So this is basically telling me what the first column should be, right? The first column should be 1, 1. That's what happens when we apply T to the first basis element. We get the sum of the two basis elements. Okay.
Why is it not 2, 1 for the column?
Because I'm writing in terms of this basis, basis. So I need to take this and write it as,
okay, I get that.
1 times 1, 1 plus 1 times 1, 0. And then I need to apply T. So that's number 1, column 1. Sorry that it's a little bit messy. Column 2, if I compute T of 1, 0, I get 1, 0. And that's just 0 times 1, 1 plus 1 times 1, 0. So I get 1, 0. So I see that I'm in Jordan canonical form. So notice that this is an example of one matrix. This is an example of taking a matrix, which is not diagonalizable, and putting it into Jordan canonical form.
That's really cool. So we ended up with a lower triangular matrix.
Yeah. Okay. Sorry. So there's an issue about ordering. So let me just go back. So all of these were everything that I wrote here is using a convention for ordering the basis. Sorry, for some reason I'm not seeing the big matrix. Yeah, all of this is using the convention where the ones are above the diagonal, and the procedure that I gave. The algorithm that I gave was carefully constructed so that it would give you the one with the ones beneath the diagonal. But that's just a question of ordering the basis. So don't worry about that. I should have just said in the beginning that the Jordan form is with ones below.
Okay. So the process that we just did just took this operator that we had and we turned it into that into Jordan form. So this is what this whole thing was describing. And we use this, we find, so we study the nilpotent matrix is what I'm assuming. Yeah, so yeah. So we take.
So you first have to figure out what the eigenvalues are. And these eigenvalues, okay, each one of them has under its control a whole part of the vector space, which is called a generalized eigenspace. Inside there are all these lemmings, which the nilpotent matrix T minus lambda will eventually kill all that. Okay, the ones that it kills right away are the eigenvectors, but there's others behind them which are eventually killed by this T minus lambda. And we call those generalized eigenvectors. So the real problem is to find all the generalized eigenvectors, okay, and to put them in an order, to order them in a specific way so that there is no, so that you basically remove any kind of uncertainty about what the operator looks like. It basically is like, you want to choose them in the simplest possible way so that the resulting matrix is
Nice.
is nice, and it's such that just by looking at it, you can tell right away if your matrix, if your two operators are equivalent or not. Right? It's like the signature, the DNA of the matrix. Because if I give you a matrix and another matrix, I could say, well, can you find a basis that makes this matrix into that matrix? Like, are they really the same operator, just with a different choice of basis? That's the problem. And the idea is that if you identify the Jordan form, then they must be the same.
That's really useful.
It's an invariant. It's an example of an invariant. It's like, it's a complete invariant. It's an invariant that gives you the complete classification of operators.
Now, in this example that we worked in, we had one eigenvalue, correct?
There was only one eigenvalue, yeah.
Yeah. So our polynomial was pretty simple. So what happens?
T minus lambda squared, yeah, T minus 1 squared.
Yeah. So what happens if we have two? We would have two factors, correct, for this minimal polynomial?
Well, okay. So what? Sorry. So the minimal polynomial is T minus 1 squared. Okay. So there's only one eigenvalue. So there's only one piece of the minimal polynomial. It's a square. It's a power of a single linear factor. Okay. Now let me give you another. Let me look at a different example just to see the minimal polynomial. So if we take, let's say, one. Oops. I don't know how that got there. Okay. So if we take 1, 1, 2, 3, 2, 4. The textbook explains how to put a matrix into upper triangular form. You can always put an operator over the complex numbers. You can put it into upper triangular form. Okay, so let's say that you did that work and you have chosen a basis which puts your operator into upper triangular form. Okay, is that okay? Can I?
Yep. Yeah.
Can I assume that?
Yeah.
Okay. So if that's the case, then look at what happens. So upper triangular form is very nice for the following reason. So it tells you something about the way the operator is acting. It's telling you that the first basis element is sent to itself. The second basis element is sent to itself, but with an error, which is the previous basis element, and it never interferes with the third basis element. So in a way, this is like, it's like, yeah, I hope that's clear. So that, yeah. That, the first few, like if you take a package of the first k eigenvectors, the first k basis elements, if you just group them together, then T sends those to themselves. It's an invariant subspace. So upper triangular means, I mean, you read this presumably, but upper triangular means that the span of E1, the basis E1 up to EK, is an invariant subspace for all k. Okay, so the first is an invariant, the first two is an invariant, the first three is an invariant, and so on, going up to the total. So, okay, so what? So what? Let's say that I want to find a polynomial that kills this matrix. Well, what I could do is take something like t minus 1. Okay, and that will be 0, 0, 1, 2, 3, 4. Okay, so I kind of like this because there's a slippery slope. Okay, the matrix like this. Okay, you could think that there's a diagonal here, but then there's a, and let's assume that it's 0 below the diagonal. Okay, then here there's a slippery slope. Okay, where if you have a matrix which has zeros down here, and if you have a few elements here up here, then when you multiply this matrix by itself, okay, these entries, they move towards the corner and they eventually get killed. Okay, so in other words, if I have something like this, right? If you just look at what happens when you square this, in the first row, what's going to happen? You're going to get nothing,
zeros.
nothing, and then 2. This, and then something. And then in the second row, you're going to get 0, 0, 0, 6, and then something, right? So the amount of zeros, they fill up to the whole matrix. So anytime that you have zeros on the diagonal and below, that thing becomes nilpotent. Okay, so that's okay. So you understand what I mean by the slippery slope?
Yeah. In this case, we're going to have an issue, correct?
Yeah, we have a problem. We have a problem. The problem is this thing here. Why do I have this here? It's because there was a different eigenvalue. Okay, so now what I'm going to do is put that one in as well. I'm going to take t minus 1, and I'm going to multiply it by t minus 2. Let me figure out t minus 2. T minus 2 is going to be like -1, -1, 0, and then 2, 3, 4. Okay, and if I take the product here, then you're going to see what's happening. So I'm going to get, then it'll be, 0, something, whatever it is, -2, 8, and then 0, 0, 0 in this case, and then 0, 0, 0. So now you see that, this one did the job of making these guys 0. This one did the job of making this one 0. And then when you take the product, these zeros kill these, and this 0 kills this. And so you get something that's strictly upper triangular.
Professor, does it need to be nilpotent?
Well, why do you think?
No. Sorry, wrong. It does. Is this a condition for it to be nilpotent, or
is what a condition?
The diagonal being 0 and everything under it.
Yeah. So any matrix that looks like that must be nilpotent. Okay.
Yeah.
But I could change the basis to a nilpotent operator, and it won't look like that. It'll look totally different. It'll look crazy, but it's still nilpotent because I just changed the basis on something that was nilpotent. So not every nilpotent looks like this because you may not be in the right basis. You need to use the result in the textbook, which says that you can take your matrix and put it into upper triangular form. Then you need to look at whether the diagonal entries are 0 or not. You see what I'm saying? Like the way that an operator looks depends on your basis. If you chose it well so that it's upper triangular, then you can just look at it and see whether it's nilpotent. You can just see whether there's zeros on the diagonal. But anyway, let me go back to the example, right? So I'm trying to build the minimal polynomial, and I have something here which is nilpotent. So that means that I'm pretty close now, right? Because all I need to do is take a certain power of this, and I'm going to get a polynomial that kills t.
Yeah.
Okay, so it turns out that because of the double eigenvalue, I need to take this thing. I mean, it could have been that this would already be 0. If I was lucky, this would already kill, but it doesn't. You have to take a square here.
Yeah.
So the idea is that in order, an algorithm for finding the minimal polynomial is put it into upper triangular form, look at the eigenvalues here, and produce t minus 1, t minus 2, and then increase the power of each one separately to see how many powers of each factor do I need in order to kill the operator. And that will give you the minimal polynomial. But later on, we're going to prove that actually, if you just use the formula of taking t minus lambda to the power of however many there are, like in this case there are 2, and you take the product of all those, then that's the characteristic polynomial, and that will always kill. So in this case, we happen to have that the characteristic polynomial is the same as the minimal polynomial. But anyway, we're going to get to that later.
Is there a term for this? I've heard algebraic multiplicity and geometric multiplicity, and I don't know if this is what they're meaning. Like
Yeah. So
I just don't know which one.
Yes, we're going to get to all that. Yeah, we're going to get to all that. So these,
So now when we do our analysis, we have the first factor to look at, right? We do it case by case. We do it for t minus 2 and t minus 1 squared.
Yeah, correct.
Okay.
Yeah. So for t minus 2, that would correspond to just looking for its null space because you're just trying to find an eigenvector. So you will find one eigenvector by looking at t minus 2. And then for t minus 1, you're going to need to do the more sophisticated procedure. You're going to need to make sure that you find a vector which is very long-lived in the sense that it takes 2 iterations for the thing to die. Then it will generate progeny of one other vector, and that will give you your basis for that. So you'll have 3 in total.
Okay, so when we have just a multiplicity of 1 for the eigenvalue, when we look at the minimal polynomial, in this case, we have that we only need to, we can do the process that we've learned before, just finding null space. But if it's a higher dimension, then we have to, okay, perfect.
That's right. But keep in mind that it is possible to have, let's say, 5 eigenvectors, all with eigenvalue 0 or eigenvalue 3. So it's possible that the eigenspace is bigger than one-dimensional. There could be many eigenvectors with the same eigenvalue, right? So that might, for example, here, if you did something like this, 1, 1, 2, right? Then the minimal polynomial of this is just z minus 1 times z minus 2. You don't need a square here. That's not necessary in order to get the minimal polynomial. So whenever there is a repeated eigenvalue, okay, there's a question: is that eigenvalue repeated because what I mean is, if you put the matrix into upper triangular form and you see a repetition of the diagonal entry, repetition of lambda, the question is that being repeated because there's genuinely 2 eigenvectors with the same eigenvalue, or is it because there's a generalized eigenspace for that eigenvalue? Either case can happen.
Okay. Yeah, I guess this is also a good example because I was just gonna, because I guess you can just blindly apply the analysis at all times. But if you have a diagonal matrix, this looks kind of good. This is better than the upper triangle, right?
Well, yeah, of course. I mean, the goal is to put this, the goal, if you want, is to put operators into diagonal form. But the problem is that some can be done that way. All you need to do is look at the null space of t minus lambda, and you get enough eigenvectors to give a basis. Okay. The whole purpose of all this, again, is when there are not enough eigenvectors and you need to have something else. And that something else is a generalized eigenvector.
Thank you. That was
You're
really
welcome.
interesting. I think I get the process now.
Yeah, you just go over it again. I mean, every time I teach it, I need to refresh my memory of the order of operations, because it's a little bit tricky to make sure that you don't pick vectors in the same space, when you should really be keeping them separate. Anyway, any other questions?
Yeah, Professor. This is you might kill me for this, but
no. I can't reach
debatable.
through. You're protected by the walls and so on.
Thank God. Then, I'm confused on exactly what a generalized eigenspace is. Like, what does it exactly represent?
Okay.
This is the whole point of this whole thing. So.
Yeah. So let me just. So an eigenspace. What is an eigenvector? Eigenvector for eigenvalue lambda. Okay, what is it? It's a vector such that TV is lambda v. You're okay with that? Do you like eigenvectors, by the way? When you see a vector that has this property, does it give you pleasure? Does it give you? Are you relieved?
Yes. Yeah, it's quite satisfying.
Yeah, I agree. Okay, but the problem is that there's a limit. You cannot necessarily find a basis of eigenvectors. Do you believe me when I say that? You have an operator. If you have an operator, right, which is acting on your vector space, it's not necessarily the case that you can find a basis where each one of them is sent to itself by the operator. Just think about what happens in finite sets. You have a permutation of a finite set. Sometimes you find a fixed point, but sometimes not. Sometimes you find a cycle of several elements which are sent to each other. Right? That behavior happens for linear operators. But you see, like, if you don't believe that, then there's no point in me going forward. So does it make sense to you that there could be an operator that does not have a basis of eigenvectors? Or is it confusing?
Yeah.
Like, like if you go through it again, this one is the fundamental example. It has a one-dimensional subspace which it sends to itself. 1, 0 is sent to itself. But anything else is moved horizontally by this operator.
Yeah, or the rotation, or the rotational matrix.
Well, okay, so be careful about rotation.
Stays.
Just be careful about rotations, because rotations do not have eigenvectors. But the reason they don't have eigenvectors is because you're over the real field. It doesn't have any real eigenvectors. Okay, but it does have complex eigenvectors. I'm talking about something more problematic than rotations. Rotations actually are always diagonalizable by a theorem that you're going to prove in 247. The problem is that in order to diagonalize them, you need to go to the complex numbers. But what I'm trying to say is that even over the complex numbers, you cannot diagonalize a matrix necessarily. There are some examples like this one, which will never be diagonalizable because they have a shifting behavior, that any vector that is not in the 1, 0 space will be moved to the side always. And so you can never find something that is sent to itself. Okay, so these things that are moved sideways, those are generalized eigenvectors. So what I'm trying to say is that to be an eigenvector means that TV is equal to lambda v. Okay, but to be a little bit a more useful way of thinking about it is that T minus lambda times the identity kills V. This is the same equation. I'm just rewriting it. Okay, so if you were lucky, then you would be able to find a bunch of numbers, lambda 1 up to lambda n, and a bunch of vectors, v1 up to vn, such that t minus lambda I vi is equal to 0. Okay, if you were lucky, then you would be able to find a basis of eigenvectors, which satisfy like this. Okay, but the problem is that, like I said, this is not always possible. So what you do is that you say, well, okay, I'm going to look at vectors which are killed, but not by t minus lambda, but by a power of t minus lambda. So what does this mean? This means that t minus lambda I v equals 0. So this is an eigenvector. Sorry, this is an eigenvector because t minus lambda I kills it. So what does that mean about v? V is not an eigenvector, but it is mapped by t minus lambda to an eigenvector. So it's like a precursor to an eigenvector. It's like something that you have to wait a little bit of time before it becomes an eigenvector. Right? So you have to apply t minus lambda I a few times. Okay, and you know, the idea for this, like why is it obvious that you should consider powers of t minus lambda? The reason is because of the minimal polynomial. The minimal polynomial looks like this. The product I is equal to 1 to k. So the minimal polynomial is a product of these things which are powers of t minus lambda. And this is 0 because it's the minimal polynomial. It kills t. So the minimal polynomial tells us that it's important to look not just for the vectors that are killed by t minus lambda, which we love so much, but you should also look for those vectors that are standing behind those vectors, which are eventually killed by t minus lambda I. It's a new phenomenon that you know, I mean, I try to motivate it with the finite sets and the cycles. It's the same phenomenon, okay? But anyway, yeah, you need to think about these different steps. Go through it in your mind, that I have an operator, I have a polynomial that kills the operator, I factor the polynomial, and then I try to look at the null space of these factors, and those null spaces are generalized eigenvectors, generalized eigenspaces.
So basically, when we say generalized eigenbasis, we're referring to the basis of vectors which basically, after applying t minus lambda multiple times, we map them to 0.
Correct. Correct. The null space of t minus lambda to the n. That's exactly what that is. So the generalized eigenspace for value lambda is the null space of t minus lambda to the n, where n is the degree. It appears in the minimal polynomial.
Yeah, I think what just got me is like, you know, when you have this map and then like we're thinking about it now from the sense that the same, like we can represent the null space of this map using a combination of other vectors which this map maps to, and that just like makes everything confusing. But
yeah.
I
mean, that's the thing, is that in order, yeah, that's right. So it's similar to yeah, that's yeah, that's right. You need to use the behavior of you need to study the behavior of the operator in order to know how to choose the basis, in order so that the basis simplifies the operator, right? So in order to choose a basis for which the operator looks simple, you need to make that basis choice in a way that's compatible with the behavior of the operator. So it's a match between the operator and the basis, right? You could think of it as that the basis is adapted to the operator itself, right? So it's, I'm not sure what it's similar to, but it's,
Can we relate this to the notion of a flag for a second? I'm just looking at chapter 8, and it says that the null space, there's a sequence of increasing.
well, what's
null
a flag? What's a flag? What do you think is a flag?
Lower dimension contained in like successively increasing dimensions until it contains all of V. Like,
Yeah,
I mean,
so this is right here. Where is it? Here. Okay, so you see here that the VI is such, the VI is exactly the null space of n raised to the 3 power. So I apply n once, twice, 3 times, and it goes to 0. Okay, so, but it goes from VI to VI, right? So if I look at the image of n, I get this subspace. This subspace is contained inside the original space. And then apply n again, and this will be a subspace of this space. So we get a sequence of subspaces getting smaller and smaller until it's 0. And so you have a flag. So definitely whenever you have an operator, the operator has eigenvalues, lambda I, and then there are these nilpotent matrices associated, one to each eigenvalue. And those nilpotent matrices define a flag on the corresponding VI. And so you get natural flags on your vector space coming from the operator. And what we're doing in the choice of basis is that we're choosing the basis so that it's adapted to the flag.
that's really cool. Yeah, because in Axler chapter 8.2, you get sequence of increasing null spaces. And so it just immediately.
Yeah, all of that. So basically what I did in today's class was I did a shortcut way of doing the rest of his description in chapter 8. So all of what's in chapter 5 and in chapter 8 is basically contained in what I did so far. The only thing is that there's an important thing that I did not do yet, which is to complete the proof of the decomposition theorem. But the thing about the flags and all of that and the indices, like what I'm trying to get across is that the basic idea for what we're trying to do is very simple, but the notation can be intimidating because of how many different indices there are. There's an index that measures which eigenvalue. Then there's an index that measures how many of these extended basis elements you have. And then there's another index which tells you how many progeny they have. So, if you really want to write everything down, there's a lot of indices, but the basic idea is quite simple. If we have some time at the end of this class, I want to kind of show you a kind of amazing way of thinking about the Jordan canonical form, which they usually, which is not usually taught. It's like an unnecessarily complicated way of seeing it, but it's a very beautiful way of thinking about it, and hopefully I'll get to that. It basically makes it look like a Tetris game. But anyway, we'll get to that hopefully.
Looking forward to it.
That's intriguing.
Any other questions before we sign off?
are we discussing minimal polynomial in class?
Uh,
And like how to find it specifically?
yeah, we're going to talk next
that
week.
too
We're going to
quick?
talk about the how many weeks do we have left?
I think
So we have 2 full weeks left. Okay, that's good. So we'll
maybe less than that. I think
I think 1.5.
1.5.
check.
Professor, we're all expecting a
Yeah, I mean,
listening
it's so.
session.
Oh my god, you know what?
Sorry, when is the last day of classes? I thought. Oh, the last day of classes is December 10. So that means that we have December 8 and 10. And we have December 1 and 3. So we have 4 classes remaining, 2 assignments remaining, and that's plenty of time. So we'll complete this theorem that we need to show. We'll talk about the characteristic and minimal polynomial some more, and I should have enough time to talk about the determinant. And the assignment should have some material on tensors. Okay, everyone, have a good weekend.
Thank you for
Thanks
your
a lot,
time.
Syed.
Have a good weekend. Thank you, Sam.
Bye.
Thank you very much.